All right, in this video, we're going to take a quick look at an introduction to some gas laws in the gases unit for advanced or regular chemistry. In this particular worksheet, number 2, we're being introduced to Boyle's law, Charles's law, and the combined gas law. Boyle's law, P1V1 equals P2V2, is an inverse relationship between pressure and volume. When you're reading a problem, if you notice that only the pressure and the volume are changing, then you know you're going to be using Boyle's law. When using Boyle's law, the temperature and the amount of gas are being held constant. In Boyle's law, there's a P1 and a P2. You can use any units for pressure as long as they're the same on both sides of the equation. There's also a V1 and a V2, and the same logic applies. You can use any units for volume as long as they are the same on both sides. The second law is Charles's law. Charles's law shows a direct proportion between volume and temperature. When volumes increase, temperatures are also going to be increasing. When doing a word problem, if you notice that only volume and temperature are changing, you know you're going to use Charles's law. The pressure and the amount of gas would be held constant. The units for volume in Charles's law are similar to those in Boyle's law. You can use any units for volume as long as they're the same on both sides. But temperatures, and this is true for all gas laws, temperatures, we have to use Kelvin temperatures. Those are absolute temperatures where there are no negative values, and we will never see a 0 Kelvin temperature. Absolute 0, the lowest possible temperature, is theoretical. You can never actually reach it in an experiment. So there's a little formula shown here. The Kelvin temperature is the Celsius temperature plus 273 or 273.15. If a question has a temperature with a rounded off whole number value in Celsius, then I usually just put 273 in the formula. If the temperature in Celsius has decimal places, then I'll include the 0.15. The third gas law is the combined gas law, and this particular one uses all three of the variables, pressure, volume, and temperature. Pressure units can be anything as long as they're the same on both sides. Volume units can be anything as long as they're the same on both sides. But again, temperature has to be in Kelvin when you're using the combined law. If you need, there are some conversion units here for pressures. If you need to convert pressure units, we can use unit multipliers to do that. So let's jump in. It would be good if you have the worksheets in front of you, you could do the questions with me. Pause the video as you need. Don't just copy and take notes. Do the question yourself if you're able. So question 1 says the volume of a gas, 15 liters, measured at STP. We remember that means standard temperature and pressure. Standard temperature is 0 degrees Celsius, and standard pressure would be any one of those pressures up above. In this question, we're talking about kilopascals, so we'll say it's 101.3 kilopascals. That's what STP is. We're asked to find pressure in kilopascals if the volume increases to 18 liters. So when you read this question, you notice that the volume is changing, and we notice the pressures are also changing. We're starting with a pressure of standard pressure, and we're trying to find a new pressure. Temperature is being held constant, and although it doesn't say it, we'll assume that the moles of gas is being held constant as well. So the way I want you to do your problems on this worksheet is to note the variables that are changing. So in this problem, pressure and volume are changing. Note for yourself the name of the gas law. This is Boyle's law. Write the gas law. So for Boyle's law up above is P1V1 equals P2V2. Now, if there's a need to convert any units, you would do that possibly at this point as well. But in this question, we don't need to do any unit conversions. So now we're going to do some algebra. The thing that we're looking for in this problem is the new pressure. So we're looking for P2. So I'd like you to do some algebra before you do any substitution with numbers. Rearrange Boyle's law to say P2 is equal to. If you divide both sides by V2, you'll find that the new pressure is P1V1 divided by V2. At this point, put your numbers with the units into the equation. The original pressure, P1, was standard pressure, so that'll be 101.3 kilopascals. The original volume was 15.0 liters. The new volume is 18.0 liters, and I just quickly note that those volume units are the same, which is good. Notice that when in this setup, the liters will be canceling. And so we're going to be left with kilopascals, which is the unit for pressure number 2. So now pause and grab your calculator and calculate the new pressure. Okay, when you do this, and rounding off to, I guess, 3 significant digits, you'll get 84.4 kilopascals. And you'll notice that that answer matches the answer that's given at the end of the question. Scroll down to question 3 and give that one a try as well. So as you read this question, we notice that the volume of a given mass of gas is 0.5 liters. So there's the initial volume. We're given an initial temperature and we're given an initial pressure. So I might be thinking right now that this could be a combined gas law question because all 3 of these things are mentioned. But let's keep reading. What will be the new volume? So the thing I'm looking for in this question is V2, right? This was V1, the 0.5 liters. This would be T1, and this would be P1. Now the question saying, what will be the new volume, V2, at this new pressure, 152 kPa? So that's going to be my new pressure, that's P2. And it says at the same temperature as well. So the temperature is not really changing, so we don't need to worry about the temperature in this problem. So we note that the only things changing are pressure and volume. That's a Boyle's law problem. Boyle's law, P1V1 is P2V2. That's the inverse relationship. We're trying to find the new volume, so we want V2. So V2 would equal, rearrange your formula. V2 would be P1V1 divided by P2. Now, do we have any problems with units in this question? The original pressure was given as torr. The new pressure was given as kilopascals. That's a small problem. The pressure units have to be the same. They can be any pressure units, but they have to be the same. So you could convert the kPa to torr, or you could convert the torr to kPa. It's up to you. I'll convert the kPa given for P2, I'll convert it to torr. So my new pressure, P2, I'll use a unit multiplier to do this, 152 kilopascals. Let's use a unit multiplier, convert those kilopascals back to torr according to our recipe up above. Okay, this is the recipe for converting pressure units. We can see that 760, now the recipe just said 760, but I'll treat that as 3 significant digits, so I'll put 760 with a decimal. Torr is the same as 101.3 kilopascals. Now would you grab a calculator, figure out what the new pressure would be in the units of torr. You'll get 1140 torr as the new pressure. So now that we have the same pressure units for P1, P2, we can put everything in and calculate the new volume. So the original pressure was 795 torr. The original volume was 0.500 liters. The new pressure, the one that we just converted, was 1140 torr. So go ahead now and calculate your new volume. Notice that our significant digits, we have 3 digits in the first pressure, 3 digits in the volume, 3 digits in the new pressure. So we're going to keep 3 digits in our answer. So I get 0.349 liters, and I think this is the only question on this worksheet where the answer that's given is wrong. The answer here, 0.166 liters, is incorrect, so ignore that answer. So there's my answer for the new volume. Notice that I knew what the answer would be in liters because the starting volume was in liters. The units for torr will cancel out, and we're going to be left with liters as the units for volume in this question. So those were 2 simple Boyle's law problems. So let's go down and try something a little bit different. Question 7. Read the question and see if you can identify which gas law we're going to use to solve that. All right, so 3 liters, that's my starting volume, I guess. V1 of hydrogen gas is at minus 20 degrees Celsius. That'll be T1. I notice it's in degrees Celsius, so if I have to use this temperature, I'll need to convert it to Kelvin before I do that. It's allowed to warm up to a new temperature. So this is the first time we're seeing temperature changing. And again, that's a Celsius temperature. We'll have to convert it to Kelvin. What's the new volume if the pressure remains constant? So I'm looking for a new volume, V2. So the things that are changing in this question are volume and temperature, and that means we're going to need to use Charles's law. Okay, Charles's law was a direct proportion. V1 over T1 was equal to V2 over T2. And we're trying to find the new volume. So what I'm looking for is this, V2. To do that, I'm going to use cross multiplication. Just to remind you what that means, if you have some fractions that are equal, so perhaps you have 5/10, that's 1/2, and that's going to equal 3/6, right? Those 2 fractions are equal. You can pick any one of the 4 numbers in that equation, so for example the 5, and you can ask, how could I find the 5 using the remaining numbers? To get the 5, you can take the numbers that are opposite from each other, the 3 and the 10, and you can multiply those, 3 times 10, and then you could divide that by the remaining number, 6. So 3 times 10 is 30, divided by 6 would give me 5, the number that I was looking for. On the other hand, if I was looking for a different number, so perhaps we're looking for the 6 over here. Again, you'd take the 2 numbers that are opposite from each other, 3 times 10, that's 30, and then you would divide by the remaining number, 5. 3 times 10, 30, divided by 5 gives me 6, right? You could do that for any of these numbers. Let's do it one more time. Suppose you were looking for this 10. To find that 10, take the 2 numbers opposite each other, 5 times 6, and then divide by the remaining number, 3. 30 divided by 3 gives me 10. So that's cross multiplication. So using that same logic here, to rearrange this formula, we can say V2 would equal the 2 things that are opposite from each other, V1 times T2, divided by the remaining guy, so divided by T1, right? So there's cross multiplication. Now we have that problem with the temperatures. We have to convert those Celsius temperatures to Kelvin. The way to convert that, the formula at the top of the page earlier, the Kelvin temperature is the Celsius temperature plus 273 or plus 273.15. In this particular question, the temperatures have decimal places, so I'm going to include the 0.15 when I do this. So T1 would be, in Kelvin, it would be the Celsius temperature, plus 273.15. So that's going to be minus 20.0 plus 273.15. That's going to equal T1 253.15, but if I round it to one decimal, 253.2 Kelvin. Do the same thing for T2. T2 would be 27.0 degrees Celsius plus 273.15 gives me 300.2 Kelvin. So those are my two temperatures converted to Kelvin. Now we can put everything into our formula. The starting volume was 3.0 liters. The new temperature, T2, 300.2 Kelvin, divided by the starting temperature, 253.2 Kelvin. We notice the Kelvin units are going to cancel, and we'll be left with liters. Grab your calculator and evaluate that. You'll get 3.6 liters. Now you might be tempted to just cheat a little bit and use the answer that's there, but don't do that. If you've made a mistake with your units or made a mistake with your algebra, you'll get the wrong answer, and you want to know that. So don't just copy the answer from above. Make sure you're grabbing your calculator and actually doing the question. Notice I'm paying attention when in my answers to significant digits. The V1 had 2 significant digits, so my answer was rounded off to 2 significant digits as well. Pause the video and see if you can do question 10. So this question says 280 liters of carbon monoxide at this temperature. So there's a V1 and a T1. It says this sample of carbon monoxide at minus 20 must be reduced in volume to 130 liters. So that's my new volume. That's going to be a V2, while its pressure is being held constant. To accomplish this, by how many degrees must the gas be cooled? Now, first of all, what variables are changing in this question? You'll notice that the variables changing are volumes and temperatures again. So this is a Charles's law problem. V1 over T1 is V2 over T2. I know V1 and V2, and I know T1. So I guess logically we're going to find T2. But that's not going to be the answer to the question. T2 will give me the final temperature, but the question's asking how many degrees must the gas be cooled to do this. So once I have T2, I'm going to then have to figure out by how much did we change the temperature. So start by doing some cross multiplying and rearrange your formula to find T2. Take the things that are opposite from each other, V2 and T1, and multiply them. It doesn't matter what order you multiply. If you want to put T1 times V2, that's fine. 2 times 3 is the same as 3 times 2. And then divide by the remaining variable, so divide by V1. Do we have to do anything with the units in this question? Well, T1 was in Celsius, so yes, we're going to have to convert that to Kelvin. So do that. Our formula is to take the Celsius temperature and add 273. In this Celsius temperature has a decimal place, so let's include the 0.15. So that's going to be, just like earlier, 253.2 Kelvin when rounded off to one decimal place. Put this into your formula. T2 would be the new volume, so it's going to be V2, which was 130 liters, 130.0 liters, times T1, 253.2 Kelvin, divided by the original volume, 280.0 liters. In terms of significant digits, it looks like we're going to keep 4 digits in this answer. Okay, and in my answer key, I've only got 3 digits. That's a little bit irritating, so let me grab my calculator and do it again. So 130 times 253.2 divided by 280. So it's 117.6, I guess. So 117.6. Now this is a temperature, so the units will be Kelvin. But that's not what we're trying to find. We wanted to know by how much did the temperature have to be dropped, to be changed to do this. So we're going to have to find the change in temperature. The change in temperature is the final temperature minus the initial temperature. So it's going to be 117.6 Kelvin minus 253.2 Kelvin. So the change in temperature will be negative 136. Well, actually, I'm going to do it again because my answer's rounded off. 117.6 minus 253.2, negative 135.6. Now that temperature change is negative because it means the temperature's dropping. So we can say cool by 135.6 Kelvin. Notice when I phrase it like that, cool by, I change the negative to a positive. The change in temperature could be positive or negative. In this case, it was negative. That meant temperature was dropping. When I say cool by, that implies dropping. So we then use the absolute value of the temperature change and say cool by 135.6 Kelvin. Now you might be a little bit confused about the units. Did it matter whether we used Kelvin or Celsius? If you're finding a change in temperature, it doesn't matter which units you use. For example, if a temperature changed from, let's say, 0 degrees Celsius to 10 degrees Celsius, you'd say the change in temperature was 10 degrees Celsius. If you were to put this into Kelvin units, that would be a change from 273 Kelvin to 283 Kelvin, and the change in temperature would have the same number. It would be 10 Kelvin. So when you're using a change in temperature, you can express it in either Celsius or Kelvin. Okay? All right. Let's go down and try question 13. Pause the video and see if you can identify which gas law we're going to use to do this. So 20.0 liters, that's my starting volume, V1, of ammonia gas at 5 degrees Celsius. There's a T1, and I notice it's in Celsius. And the pressure, P1, is given in atmospheres. Calculate the volume, so I'm going to be finding a V2 at this temperature, and it's a different temperature, so T2, and a different pressure, P2. So this question, all three things are changing. So PV and T are changing. When all three things are changing, we're going to be using the combined gas law. The combined law says P1V1 over T1 is equal to P2V2 over T2. So what we're trying to find is V2. So rearrange your formula by cross multiplying. This one's a little bit trickier because there's more variables, but the V2 that I'm looking for is there. What I'm going to do is take the things opposite. So I'm going to take all of these things that are opposite and multiply them. Then I'm going to divide by whatever's left. So I'll be dividing by the T1 and the P2. So let's give it a try. The V2 will equal P1 V1 times T2, the things that were opposite from each other, divided by the things that are left. So divided by the P2 and divided by the T1. Okay, so there's my formula. The only thing I really have to, actually there's a couple things I have to worry about. My Celsius temperature has to be converted to Kelvin, and I notice the pressures are different units. That's a problem. They have to be the same units to put them into the formula. So pause the video, convert your temperature to Kelvin, and convert one of those pressures to the same units as the other one. So my temperatures, T1, would be 5.0 degrees Celsius plus 273.15. I'm keeping the 0.15 because the Celsius has decimal places in it. That's going to be 278.2 Kelvin. My T2 is 50.0 degrees Celsius plus 273.15 is 323.2 Kelvin. So those are my temperatures converted. And then I'll take my atmosphere pressure and I'll convert it to kilopascals. If you did it the other way around, if you switched your kilopascals to atmospheres, that's fine. You'll get the same answer as me in the end. So my P, what am I doing? I'm going to be taking my P1 and converting it to kilopascals. So 0.969 atmospheres with 1 unit multiplier. Switch those atmospheres to kilopascals. 101.3 kilopascals is 1.000 atmospheres. So that gives me 98.2, 3 significant digits, kilopascals. Now that my units are all good, I can substitute into my equation. V2 will equal 98.2 kilopascals. That was my P1 times V1, which was 20.0 liters, times T2, 323.2 Kelvin, divided by P2, which was given in the question, 107 kilopascals, times T1, which was 278.2 Kelvin. Now a little calculator tip. In this question, what I would do on my calculator is I would multiply everything in the numerator. So 98.2 times 20 times 323.2. Then I would divide by 107. And then I would divide again by 278.2. Dividing twice because the things in the denominator here are being multiplied together like that. So it's easy on a calculator to just multiply everything on top and then divide by the first thing and divide again by the second thing in the denominator. There are other ways to do that, but that's how my brain works. And I get 21.3 as my new volume, and the units are going to be liters. Right? It's a little bit different from the answer that's given here, probably because of rounding issues, or I'm a little neurotic with my significant digits and the author of these worksheets may not have been. Okay, we'll do one last question, number 15. Pause the video and see if you can do it yourself. Right, so we're finding a temperature to convert 10 liters, so there's my V1, of helium at 100 Kelvin, so that would be T1, and 101.3 kPa, that would be P1, to a new volume, that's a V2, and a new pressure, that's a P2. So it looks like in this question, all three variables, pressure, volume, and temperature, are changing. So this is going to be a combined gas law problem again. So P1 V1 over T1 is P2 V2 over T2. When you look at the units in the question, The volume units are the same. They're both liters. That's good. The temperature unit was given in Kelvin, so I don't need to convert it. The pressure unit, the one pressure is in kilopascals, while the other pressure is in millimeters mercury. That's going to be a small problem. You can use any pressure unit, but they have to be the same. So what I'll do is I'll convert them both to millimeters mercury. So 101.3 kilopascals. Well, this is actually pretty easy. That's standard pressure. So I really don't need to use a unit multiplier. Standard pressure in millimeters mercury would be 760.0 millimeters mercury. If you want to do a unit multiplier, you could, but I recognize that that was standard pressure. Now let's do our algebra. The thing I'm looking for is the new temperature, so I want T2. So if I do my cross multiplication, T2 would equal, take the things that are opposite from each other, so in this case, all of this, and multiply them together. So P2 times V2 times T1, and then divide by everybody else. So divide by P1 and V1. Now let's put our numbers in. P2 was 1520 millimeters mercury times V2, which was 20.0 liters, times T1, 100.0 Kelvin, divided by the original pressure, which was standard pressure, and that's being multiplied by the original volume, which was 10.0 liters. Grab your calculator. The new temperature is 400 decimal Kelvin. Notice, though, the question said express it in Celsius. Well, our formula was that the Kelvin temperature is the Celsius temperature plus 273.15. So if you want the Celsius temperature, you'd have to subtract 273.15 from the Kelvin temperature, right? So that I'll take my 400 Kelvin and subtract 273.15. I guess, in this case, the Kelvin temperature has no decimal places, so I'll just put 273 for that, equals 127 degrees Celsius. Right, so this is how I want all of your answers to look, right? So you're going to tell me which variables were, let me just change the color here of my pen, which variables were changing. Then you're going to write down the correct gas law. If there's any need to convert units, you'll show that. You'll rearrange your formula using algebra. You'll substitute into your formula including the units. The reason to include the units is you'll be able to see if you forgot to convert a unit. Maybe you didn't notice that the units were different for pressure. You'd be able to see that at this point. And then you put your answer with correct significant digits and units, and then just make sure you look back at the question and be sure you've actually answered what they were looking for. All right? So I hope this helps introducing basic problem solving in gas laws. Things will get more complicated later, but this is a good introduction. Good luck.